Hello, and welcome to this brief presentation on Pythagoras' theorem. Pythagoras' theorem relates to right-angled triangles, as shown in the sketch here. Pythagoras' theorem states that the square of the hypotenuse, shown as C in the diagram, is equal to the sum of the squares of the other two sides. We'll be using Pythagoras' theorem throughout this presentation and we'll be transposing the equation as required. Pythagoras' theorem states that in any right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. So considering the right-angled triangle shown here on the right-hand side, this side here has a length of 3 units. So if we square 3, we get the value of 9. 3 squared is 9. This vertical side here has a length of 4 units, and if we square that, we get 16. This longest side, often called the hypotenuse of the triangle and opposite the right angle, has a length of 5 units. If we square 5, we get 25. So in symbol form, Pythagoras' theorem states, so from the triangle above, that's 5 squared on the left-hand side, is equal to 3 squared plus 4 squared. In other words, 25 is equal to 9 plus 16. So one of the main things to note there is that Pythagoras' theorem applies to right-angled triangles only. It does not apply to non-angled triangles. So Pythagoras' theorem will allow us to find the unknown side in a right-angled triangle if we're given the values of the other two sides. So again, looking at Pythagoras' theorem applying to the right-angled triangle in figure 1, we've labelled the hypotenuse side in this particular triangle side length C. Note for reference that the hypotenuse side is always the longest side of the triangle and it's always opposite the right angle. It does not matter which of the other two sides are called A and B. I'm going to call this side A and this side B. So for this particular triangle shown in figure 1, Pythagoras' theorem here will be C squared equals to A squared plus B squared. If we want to find the length of the hypotenuse in this particular case, then square rooting both sides, C is equal to the square root of A squared plus B squared. But in this particular diagram, I've shown that C squared is hypotenuse, so Pythagoras' theorem is C squared equals to A squared plus B squared. But in each case, we're saying the hypotenuse squared is equal to the sum of the other two sides squared. Example 2 shows an illustration of a triangle ABC where angle B is 90 degrees. Angle B shown as 90 degrees in the sketch. The length of side A is given as 42 millimeters. This is shown as angle A, so side length A is opposite angle A, so there's my 42 millimeters. And side length C is stated as 37 millimeters. This is angle C, so opposite angle C we will find side length C. 37 millimeters. B in this case is the longest side, so that's the hypotenuse. So writing Pythagoras' theorem for this triangle, we would write B squared is equal to A squared plus C squared. And because we're trying to find in the question side length B, then I would simply square root both sides, so B in this case is equal to the square root of A squared plus C squared. Putting the numerical values of A and C into the equation and evaluating, hypotenuse side is 55.97 millimeters long. That's a very straightforward approach to applying Pythagoras' theorem. Here are some tutorial exercises. In exercise 1, we're given a triangle ABC, where angle A in this case is 90 degrees, and we're given the lengths of side A, which is 6.4 centimeters, and the lengths of side B, which is 5.2 centimeters. We're asked to determine the lengths of side C. Exercise 2 is broken down into 3 separate parts here. We have triangle 1, triangle 2 and triangle 3. We're asked to calculate the values of side x in each of the triangles shown. So in triangle 1 we've got to find the value of x here, which is the hypotenuse. In triangle 2 we've got to find the length of this side labelled x. And in triangle 3, slightly more complicated, we've got to find the lengths of side x shown here. I would encourage you to stop the presentation and attempt these questions, but I will work through the full solutions on the following slides. So solution for exercise 1, we're given that the triangle ABC has a right angle at A. So sketch my triangle, and I encourage you to always sketch triangles in these questions. There's my triangle. From the information in the question, this would be angle A. It doesn't matter which I call angle B or C, so I'll call this angle B and this angle C. Don't forget the way we label the triangles, the sides are opposite the angles. So if this angle A, this would be side length A. This is angle B, this would be side length B. This is angle C, this would be side length C. We're given in the question that side length A is 6.4 centimeters, so hypotenuse is 6.4 centimeters, and side length B is 5.2 centimeters. We've got to determine the lengths of side C. So applying Pythagoras Theorem to this triangle, the square of the hypotenuse, that's labelled as A squared, is equal to the sum of the squares of the other two sides. So in this case that will be B squared added to C squared. So in this case I will subtract B squared from both sides, the positive B squared there. So A squared minus the B squared is equal to C squared. Just turning the equation around, so C squared is equal to the A squared minus the B squared. Then square root in both sides, C is equal to the square root of A squared minus B squared. So I've shown that using the algebraic terms. You could, if you wanted to, put the numbers in to this equation and rearrange it numerically. Therefore, inserting the values, A squared in this case is 6.4 squared, and we're subtracting from that B squared, 5.2 squared. So therefore, C is equal to 3.731 centimeters. Exercise 2, triangle 1 here. We've got to find the value of x, and we can clearly see x is the hypotenuse side of the triangle. So applying Pythagoras Theorem, the square of the hypotenuse, x squared in this case, is equal to the sum of the squares of the other two sides. So that would be the sum of 8 squared and 15 squared. So x squared is equal to 289. The square root in both sides, x is equal to 17 millimeters. In triangle 2, we're given the hypotenuse. We can clearly see it 13 centimeters, the longest side of the triangle, and we've got to find this side labelled x. So applying Pythagoras Theorem to this triangle, we would get 13 squared, the square of the hypotenuse, is equal to the sum of the squares of the other two sides. So that would be 5 squared plus, in this case, x squared. Rearranging the equation, subtracting 5 squared from both sides, 13 squared minus 5 squared is equal to the x squared. And just turning the equation around and square rooting, then x is equal to the square root of 13 squared minus 5 squared. So therefore x is equal to 12 centimeters in this case. Exercise 2 is slightly more complicated. We've got to find the value of x again, which relates to this dimension here between D and B. So to do this, we have to break the problem down into two triangles. So we're going to consider the first triangle, that's shown as AC to D here. It's a right angled triangle, and we're given two sides of the right angled triangle, so I can find the third side. So in other words, I'm going to find this side here, between A and C. And once I've found side length AC, I can then use triangle ABC to find side lengths C to B, because I know side length A to B. And then finally I can subtract from side lengths C to B 12 to give me the lengths of X between D and B. So that's my thinking approach through the problem. So step 1, we're going to consider the first triangle, and I'll sketch it here. 20, 12, and I'm trying to find side lengths A to C. Applying Pythagoras Theorem to this right angled triangle, that would be 20 squared is equal to 12 squared plus, I'll call it AC squared. Rearranging as shown on the previous slide, that would give us AC squared is equal to 20 squared minus the 12 squared. Square rooting both sides, AC is equal to the square root of 256, which is equal to 16. So now we know side length AC has a value of 16. So now in step 2 we're going to consider the purple triangle shown above. I've just sketched it here for convenience. So again, applying Pythagoras' theorem here, we would have 36 squared, the hypotenuse squared, is equal to sum of the two sides squared, so that would be 16 squared plus CB squared. And rearranging the equation, CB squared is equal to the 36 squared minus the 16 squared. Square root in both sides, length CB is equal to the square root of 1040. That's equal to 32.25 to 2 decimal places. And our final step here is now to find the value of x, and x is equal to the lengths of CB, from which we subtract 12. So in this case CB is 32.25, and we're subtracting from that 12, so CB is equal to 20.25 units. Here are some basic triangle terminology which I'm sure you've heard before, but just for recapping, we know now that a right angled triangle has one of its sides to be a right angle, and the side opposite the right angle is always called the hypotenuse, as shown in this triangle. This is the right angled triangle. So here's the hypotenuse side, the longest side of the triangle opposite the right angle. I'm also sure you would have heard of the isosceles triangle. This is where two sides and two angles are the same. In the sketch of the isosceles triangle, this side and this side are shown to be of the same length, and this angle and this angle are shown to be the same value. But we can form a right angle by bisecting the angle at the top of the triangle, drawing a line vertically down gives a right angle. And finally, an equilateral triangle has all of its sides equal and all of its internal angles equal. They're actually 60 degrees. Again, bisecting this angle here, we can form a right angled triangle within the equilateral triangle. Here are some tutorial questions I would encourage you to attempt. Question 1a to question 3a shown here. Read the questions very carefully, particularly questions 2 and 3 here, and make sure you extract the information from the question and understand what the question is asking you to do and what the context is. The answer is shown in the brackets on the right hand side. I would encourage you to stop the presentation and attempt these questions, but the full work solutions are shown on the following slides. In question 1 we have two holes that are bored in the plate shown, and the dimensions are given on the diagram. We've got to calculate the length C. As we've got a right angled triangle and we know two sides of the right angled triangle, we can use Pythagoras theorem to find the third side, labelled C here. In this case the hypotenuse is C squared, and that's equal to the sum of the other two sides squared. So in this case that's 21.53 squared added to 31.78 squared. So C is equal to the square root of 1472.5, which is equal to 38.39 to 2 decimal places. The answer in question is given to 1 decimal place. In question 2a, we need to be very careful how we read the question. It says that a square tin of sweets has a side length of 170 millimeters. We've got to find the length of the ribbon across the diagonals. So taking that portion of the tin, this is the ribbon on the hypotenuse across here. I will call that x in this case. And as a square tin has size of 170 millimeters, then each of these sides here are 170 millimeters. So applying Pythagoras Theorem here, the square of the hypotenuse, that's x squared, is equal to the sum of the squares of the other two sides. So that's 170 squared plus 170 squared in this case. So square rooting both sides, x is equal to 2 multiplied by 170 squared, or square rooted. Therefore x is equal to 240.4 millimeters, or nominally 240 millimeters. In question 3a, we're given a concrete post labelled TY in the diagram. It's supported by 2 wires. One of the wires here is XY, the other wire is YZ, and they have the same length. We've got to determine the lengths of each of the pieces of wire to the nearest centimetre. So sketching the problem from the information given, I've got to find the value of XY in this case, because that's the length of the wire. Notice the length XT across here will be 97.5 centimetres. That's half of the 195 centimetres given in the question. We can now see we've got a Pythagoras Theorem problem. We're trying to find the side lengths xy of a right angled triangle and given the other two sides. So applying Pythagoras Theorem, xy squared is equal to, in this case, 108 squared plus the 97.5 squared. Evaluating xy is equal to 145.5 centimetres, or to the nearest centimetre, xy would equal to 146 centimetres. The answer given here in the question is actually to 1 decimal place, but we have to give the answer to the nearest centimetre, so that will be 146 centimetres. Tutorial questions continued. Question 4a, question 5a, again some practical context questions. Again, I would encourage you to stop the presentation and attempt these questions now. And again, the answers are shown in the brackets on the right hand side. Solutions to these questions are shown on the following slides. Question 4a, we're given a dormer window of a house, shown in the sketch. We've got to calculate the length of the roof over the dormer window from the ridge to the gutter. Notice this is the ridge shown here, this is the gutter shown here. So we're trying to find this length highlighted in green. Just note for reference that the roof over the dormer window is actually an isosceles triangle, where this side and this side of the roof are the same length. So dropping a vertical line down here, we can form a right angled triangle here. I re-sketch the right angled triangle for convenience. This would be my sketch, and I'm trying to find this side of the triangle shown here. I'm going to call that value x, so it's the hypotenuse of the triangle, so applying Pythagoras' theorem here, x squared is equal to 0.9 squared added to 1 squared. So square root in both sides, x is equal to the square root of 1.81, and that's equal to 1.345 meters to 3 decimal places. Question 5a, we're shown a side view this time of a dormer window. We're asked to determine how far the window projects from the roof of the house. So in other words, we're trying to find this distance across here. So just getting the problem for convenience here, this is the triangle we're looking at. So this is a right angle triangle, clearly see the right angle here. And I'm trying to find side length x as labelled in the diagram. So from Pythagoras' theorem, in this case the hypotenuse is 2.78, so 2.78 squared is equal to the sum of the other two sides squared, so that's 2.2 squared added to x squared. Rearranging the equation, x squared is equal to 2.78 squared minus the 2.2 squared. Square root in both sides, x is equal to the square root of 2.8884, which is equal to 1.7 meters to 1 decimal place. I will leave you with some further tutorial questions. Question 1, we're given a triangle CDE, in which case D is the 90-degree angle, and we're given sides CD and side CE. We need to sketch the triangle here and label the sides appropriately, because D must be the right angle and all the other sides and angles will follow from that. And you need to find the lengths of side DE in this case. Question 2 is fairly straightforward, but it's confusing the way it's written. Triangle PQR is an isosceles triangle, so be careful, we defined that a few slides previously, where Q is a right angle. Now what confuses students in this particular question is they're not used to an isosceles triangle having a right angle in it, but this one does. So you need to sketch that appropriately. Angle Q is a right angle. We're given the hypotenuse of the triangle. We've got to find in part A the value of angle QPR, in other words that's the angle at P as you've labelled your diagram, and also part B we've got to find the lengths of sides PQ and QR, and of course because of an isosceles triangle they will be the same. So to help you solve this problem, sketch an isosceles triangle where angle Q is labelled as 90 degrees and the other angles are labelled as P and R. From there, define the hypotenuse. You're given a hypotenuse side in a triangle, and then break the triangle down into a right angled triangle and solve appropriately. In question 3, a lady cycles 24 kilometres due south and then 20 kilometres due east. A man starting at the same time and from the same place, that's quite key to the problem, cycles 32 kilometres due east and then 7 kilometres due south. We've got to find the distance between the lady and the man after they finish their cycle rides. Again, this hinges very much on drawing an appropriate diagram. Both the lady and the man start from the same point on the diagram you're going to draw, and you need to draw the diagram proportionally in the direction shown that the lady cycles and the man cycles. You've then got to find the distance between their two end positions. Some students again struggle with this. They end up trying to find non-right angled triangles, but there is definitely a right angled triangle for you to find to help you solve this problem. When you see it, it will be quite a straightforward solution, but it's seeing the right angled triangle in the problem. But the key here is to draw appropriate diagram. The answers to the question are shown in the brackets here on the right hand side. Here's the bibliography used to help generate this presentation. I hope this has been of interest to you, and thank you for viewing.